And our final talk for today, it is a pleasure to introduce Professor Sergio Lopez-Permouth from Ohio University. The title of the talk, Entangled Polynomials. Please.
Hello, everyone. Thank you for the opportunity to participate in this nice conference. It's always an honor to be included. And can you see my screen now?
Yes, very good.
Okay, very good. This is a historical first for me because I always do handwritten notes, very colorful and stuff like that. And this time I thought it was time to give in to the pressure and appear professional. So I hope they turned out okay. Okay, so the title of my talk is Entangled Polynomials. That's a little bit of a sneaky title because entangled, has other meanings. But I think it makes sense, although it's not what you think. This is a collaboration with my postdoc, Q Sang Lee, and my dear friend André Leroy from University of Lens in France. So a motivation is that you can think of polynomials, just regular polynomials in a single variable, and you can think of them as infinite matrices. You take a polynomial, f0 plus f1x plus f2x squared, and so on, and you put the coefficients in the first row. So this is a finite row. After a while, you have zeros. And then you put the same coefficients in the second row, but you shift them to the right one spot. Do the same thing, then you shift it 2 spots. And the algebra that you create with these objects, with these row and column finite matrices, is isomorphic to the polynomials. And this is easy to see because if you think about it, what these matrices are, they're representations of multiplication by f of x with respect to the standard basis, the transposes. But so this makes sense. And one day we were thinking, what if you, instead of taking one polynomial, you take several polynomials, 2 polynomials, 3 polynomials, or whatever, n polynomials. And if you do that, then you could take your first polynomial, f1, and put its coefficients here. Then you take the second polynomial, f2, put its coefficients here. When you get to the nth polynomial, because I'm going to be doing arithmetic modulo m, I'm calling it the 0th polynomial. That just makes the formulas work nicer. And you put the coefficients here. And when you run out, then you just do it again. The first polynomial, the second polynomial, the nth polynomial, and you keep on going like that forever. And so we if you have 2 of them, you call them 2 nomials. If you have 3 of them, they're 3 nomials. In general, they are m nomials. And we started playing with this for reasons I will mention in a little bit. But then a former student of mine, Steve Szabo, who is a very smart guy, pointed out that there's this anisomorphism, and I can do the proof, and I believe it's true, but I still marvel at how Steve just looked at it and he said, why don't you just do it this way? And what you do is you take your first polynomial, and then you just look at the terms that are powers, the exponents are multiples of n, and then you put the terms whose exponents are congruent to 1 modulo n, and so on. You do the same thing in the second one, but with a shift. You put those things that are congruent to m in the diagonal, and you go cyclically. Finally, in the last one, you have the things that are congruent to m here, and you go cyclically, 1, 2, and so on. And that is isomorphic to it. And so we refer to this as the finite representation, because instead of having these huge matrices, now you have n by n matrices representing these objects. So here's an example just so that you wrap your head around it. This is going to be a trinomial, 1 plus x to the fifth, 1 plus x squared plus x cubed, 1 plus x squared plus x to the fourth. The finite representation would be here. So this is 0, it's congruent to 3, 1 is congruent to 1, and 5 is congruent to 2. Here, 0 and 3, the exponents are congruent to 3, 1 is congruent to 1, 2 is congruent to 2. 0 is congruent to 3, 4 is congruent to 1, 2 is congruent to 2. So you wrap these things around, and this constitutes an algebra, and it's called the algebra of trinomials. And there are 4 nomials and 5 nomials and so on. So this started some years ago. I was advising Ashley Pallone was my student at the time. We wrote the first paper. It appeared in Rendiconti del Circolo Matematico di Palermo. And at the time, my obsession, continues to be a little bit of obsession even today, is on something we call amenable basis. And we were looking for things that kind of behave like polynomials, but were not exactly polynomials. Lack of commutativity was a nice property, and so these entangled polynomials were a nice place to play. And we wrote another paper which was central to Ashley's dissertation, and it's going to appear soon in the proceedings of one of the LANS conferences. So once again, going back to this, at the time, by the way, we only had coefficients in a field. In the latest project, which is the real center of today's talk, we use R instead of K. But so these are just the regular polynomials. Polynomials are one-nomials. Every one-nomial can be thought of as a two-nomial, because having 2 polynomials will take 2 copies of the same one, or 3 copies, or 5 copies. And if you have a two-nomial, you can also think of it as a four-nomial, because take your 2 polynomials, but take them twice, and so on. So you have this lattice, it's a divisibility lattice, and you can create these larger and larger algebras, and you can actually have a direct limit. I didn't put it in the picture. I was telling you it's the first time I do PowerPoint slides, so I didn't know how to put this guy, but it's called K infinity. And that guy, it's not specific to any M, and so that's the algebra of entangled polynomials. So entangled is like a generic word when you don't want to mention a specific M.
Там где-то печень, вот это без метастазов, там легкие отдельно, много градусов.
I don't know if that was an accident.
Мікрофони, будь ласка, виключіть. Please mute your microphones.
Okay.
Yes, so sorry for interruption.
That's okay. I thought they were overestimating my ability to speak English.
Там яма была. Яма.
So here's another motivation. These were some of the early things. When you think of 1 plus x squared as an infinite matrix, then it's 1, 0, 1. Then, down the diagonals, you have 1, 0, 1, 1, 0, 1, 1, 0, 1. It turns out that you can factor this as the square of this matrix. And this matrix looks a lot like a polynomial, but there's changes between the odd rows and the even rows. And that's really the first example where we thought, this is really neat. You have an irreducible polynomial, say, over the rationals, but in this slightly larger universe, it can be factored. And so that was one of the original motivations, that this could be an interesting toy. And in fact, right now I have another PhD student, Isaac Aguillet, and a postdoc, Asam Mosafarika, and another graduate student. And we have been playing on this notion that you take an irreducible polynomial and you factor it in this bigger world. And we are even using the word valence to say that's the smallest value of m, such that if you look at the reducible polynomial as an m-nomial, then it becomes reducible. And we are still working on it. We don't have a paper ready, but some of the results are interesting. And just as an illustration here, take 1 plus x squared. This is one of the irreducible polynomials with Einstein's criterion. And it's irreducible, so the valence is not 1. If you express it as a two-nomial, you cannot factor it. We can prove it. But if you write it as a three-nomial, I'm using the finite representation here, then yes, you can factor it. And so the valence of this guy is 3. That's just a little teaser. Another motivation, if you have heard me before, you know, sometimes I like to fiddle with coding theory. And we were thinking, you know, if these m-nomials are kind of like polynomials, well, a lot of coding theory happens in quotients of rings of polynomials. There is something called cyclic codes, and they're always ideals of this quotient of the polynomial ring. So we started looking at analogous things where with quotients of the rings of m-nomials, and we got something that they call quasi-cyclic codes. Quasi-cyclic codes are very important to coding theorists, and there is not a satisfactory unified theory. Well, we don't have a unified theory, but we have a very mechanical way in which you can produce these things, and that is interesting. Right now, my PhD student Isaac, another PhD student Man-Tang Go, and my postdoc and I we're working on these connections. I was going to show you a nice table, but I couldn't put it in the slides. But there seems to be a fertile area there to get things. But now let me finish my talk with what I really announced I was going to talk about, and this is my collaboration with Q-Sang Lee and Andre Leroy. And as a motivation, let's go back to the finite representation we were looking at. This is from a previous slide. And somebody, you know, could say, well, how about the much simpler thing that you say 1, 1, 1, that's the constant term. 1, 1, 0, that's the linear term. 0, 1, 1, that's the quadratic term, and so on. Why don't you just do that? And the problem is that, well, that is the correct object, but algebra is not just about the objects. Algebra is about the way they combine. And so, yes, my three nomials look like polynomials over the direct product of the coefficients, but they don't multiply that way. But that's a situation that is somewhat familiar. That's what skew polynomial rings do. They look like polynomials, but they multiply differently because there is an automorphism. And so once you stop to think about it that way, this is not too surprising. Skew polynomials are entangled. If I start with a skew polynomial and I have an automorphism that is of local finite order, then the skew polynomial ring I obtain is going to be a ring of entangled polynomials. And kind of conversely, entangled polynomials are skewed. In fact, this is the previous relationship here is an isomorphism. So the m-nomials can be thought of as polynomials with coefficients which are vectors, and there is an automorphism, and the automorphism is just an M cycle. A nice corollary to this, if you start with skew, you go to entangled, then from entangled, you go to a very specific skewed. That means that if you start with an arbitrary skew polynomial ring that has an automorphism of finite order, say, then you can embed it into one where the automorphism is rather concrete. It's just an M cycle. And I get a kick out of this corollary because it makes me think of something, as fundamental as the Cayley theorem in group theory, where you say, I have a group of permutations. Well, that's kind of concrete, except that it's very general. I'm sorry, you have a group, an arbitrary group, that's very abstract. And then you can think of it as a group of permutations. That makes it kind of concrete. So this is similar, that if you have an arbitrary automorphism, but it's a subring of one where the automorphism is an M cycle. What other things did we get? Well, we wrote a paper. It's being considered right now. Let's hope it gets accepted. We analyze things that you would expect. Can these guys be Artinian? No, they're not Artinian. Well, polynomials are not Artinian either. When are they noetherian? If and only if the ring of coefficients is noetherian, right or left. How about the Jacobson radical? Well, the Jacobson radical of the M nomials is going to be contained on polynomials whose coefficients are in the powers of the Jacobson radical. So in particular, if I have Jacobson semi-simple, it will depend on the ring of coefficients. So the behavior is rather good. In the previous project, we had talked about units and idempotents and stuff like that. It's all interesting. I didn't want to take too many chances that I would run out of time. And so let me just finish with one thing. If you're familiar with the work of Andre, you know that he is an expert on evaluations of non-commutative polynomials. So once Andre joined the project, we just had to tackle ideas about how do you plug things into M-nomials. Do M-nomials have roots? And so we got this nice theorem. It's a little bit technical, but it seemed like a good way to conclude the talk, saying if I create an M-nomial and I have roots for each one of these M-nomials, and then these roots do satisfy some relations between them, then the M tuple will be a root for the M-nomial. And with that, I thank you for your attention. And the last thing I'm just going to show you is, once again, being honest, these are the two papers that exist in the literature. This one hopefully will be accepted soon, and then it'll be official. And these are the two that we're working on as potential applications to coding theory and to understanding factorizations of irreducible polynomials in the larger context. Thank you so much for your attention.